When we talk about the most mysterious and extreme objects in the universe, black holes usually steal the spotlight. They are terrifying, fascinating, and almost myth-like in the way they consume everything, even light. But what if black holes are not the final word on cosmic monsters? What if there is something even stranger? Something that looks exactly like a black hole but is built in a completely different way. Some scientists believe such objects could exist, and they've given them a name that sounds like science fiction gravastars. A gravastar, short for gravitational vacuum star, is still just a theory. We haven't seen one, but the math behind them makes them worth considering. To imagine a gravastar, let's go to the end of a massive star's life. A star many times larger than our sun burns through its fuel and can no longer hold itself up against gravity. When this happens, the star collapses. In most cases, this collapse leads to either a neutron star, a city-sized sphere of incredibly dense matter, or, if the star is big enough, a black hole. But in the gravastar scenario, the collapse takes a bizarre turn. Instead of crushing matter down to an infinitely small point of singularity, the star collapses into a bubble of pure energy. This bubble doesn't keep shrinking. Instead, the outward pressure of the vacuum energy inside balances perfectly with the inward pull of gravity, creating a strange cosmic shell around a void filled with unimaginable power. From the outside, this object would be nearly indistinguishable from a black hole. It would still bend light, distort time, and pull in matter with inescapable gravity. But the inside tells a completely different story. Instead of an event horizon leading to a singularity, a gravastar would have a thin shell of exotic matter wrapped around a core of vacuum energy. This shell could be only a few meters thick, yet tougher than anything we know in physics. Imagine stretching a rubber band that resists with incredible force. Now multiply that resistance by the energy of a star exploding, and you're still nowhere close to the strength of a gravastar's shell. Inside, things are even stranger. Ordinary space is not truly empty, it contains tiny amounts of energy, a background hum that quantum physics says is always there. But inside a gravastar, this vacuum energy is turned up to cosmic extremes. It's as if the very fabric of space has been supercharged, holding incredible pressure. This inner energy pushes outward while gravity pushes inward, locking the gravastar into balance. It's a cosmic stalemate frozen in time, a bubble that nature might use to avoid the paradoxes created by black holes. Now, what would happen if you fell toward a gravastar? Sadly, it wouldn't be any better than falling into a black hole. As you approached, the gravity would stretch and squeeze you, pulling at your body until you were reduced to a long, thin strand of process. Scientists dramatically call spaghettification. But instead of slipping past an event horizon into a bottomless void, you would collide with the gravastar's shell. That thin but indestructible layer would tear your atoms apart, breaking you down into fundamental particles that would then become part of the vacuum energy inside. To an outside observer, though, it would look almost the same as falling into a black hole. You'd vanish without a trace. So why even consider gravastars if they look so similar to black holes? The answer is that black holes come with big problems. They may be elegant in theory, but in practice, they break the rules of physics. A singularity is a place of infinite density, where our current understanding of science completely fails. On top of that, black holes raise the so-called information paradox. If matter falls in and is destroyed, what happens to the information that matter carried? Physics says information cannot be destroyed, but black holes seem to do just that. Gravastars could solve both problems. They replace the singularity with a bubble of vacuum energy, and their shells might preserve information in ways black holes cannot. In other words, they could keep the universe's rulebook intact while still behaving like black holes from a distance. But here's the real question. If gravastars exist, how could we tell them apart from black holes? For most everyday purposes, they act the same. Their gravity is the same, their appearance is the same, and even their terrifying effects on nearby matter are the same. Yet, there might be one subtle clue. When black holes collide, they send out ripples in spacetime called gravitational waves. We've already detected these with massive observatories, like LIGO and Virgo, which measure tiny distortions in space caused by these cosmic crashes. The signal from two black holes merging is sharp, like the thump of a bass drum. But if two gravastars collided, the result might be different. Their shells and vacuum energy could cause the signal to echo like the reverberation of a gong after it struck. If scientists can detect these echoes in future gravitational wave events, it could be the first hint that gravastars are real. The beauty of science is that even if gravastars don't exist, thinking about them expands our imagination. For decades, black holes themselves were thought of as almost too wild to be real, mathematical curiosities rather than real objects. It took generations of better telescopes, more sensitive instruments, and new discoveries to finally confirm them. Now, we VEA photographed the shadow of a black hole and heard the sound of their collisions through gravitational waves. Gravastars could follow the same path starting as theory, debated fiercely, then maybe one day becoming reality. Whether or not gravastars exist, they push us to confront how little we truly know. The universe is full of surprises, and time after time, what once seemed impossible has turned out to be real. Gravastars challenge our assumptions, showing us that even something as seemingly well understood as a black hole might not be the full story. They remind us that the cosmos may have layers of complexity we haven't yet begun to uncover. In the end, gravastars are more than just hypothetical objects. They represent curiosity, imagination, and the willingness of science to question itself. They may turn out to be real, or they may simply be a stepping stone toward an even stranger discovery waiting for us out there in the dark. Either way, they remind us of a simple truth. The universe is not only stranger than we imagine it, stranger than we can imagine. And that is what makes exploring it so endlessly fascinating.